I want to now talk about a topic that's really near and dear to my heart, in part because it was the focus of my PhD research. That's the topic of catalysis. Now, we've used catalysts at other points in this semester, for instance, to make the elephant's toothpaste reaction go at a reasonable rate, but we didn't really talk very much about what catalysts did and how they behave. Let's start by thinking back to that elephant's toothpaste reaction. When we added Ki, the reaction went absolutely crazy. Foam went everywhere. It was very dramatic. How might we determine which part, the potassium or the iodide, was the catalyst? Catalysts, as we're about to see, can be a little bit tricky. One possibility would be to test each of the individual ions separately. There were only 3 things in the solution we added to make the reaction go. There were potassium ions, iodide ions, and water. Now, the peroxide was already in water, so we can be pretty confident that that wasn't it. But by adding sodium iodide, we can test if the iodide is the catalyst. And by adding potassium nitrate, we can see if the potassium is the catalyst. If you do this experiment, what you see is that the sodium iodide likewise makes the reaction go bonkers, but by comparison, no reaction occurs with the sodium nitrate. So just as reaction rate laws need to be determined experimentally or from advanced calculations, the same is true for identifying catalysts. More information than just what is given in a chemical reaction equation is necessary to identify a catalyst. So now let's talk about what a catalyst is and why it might be challenging to identify one. A catalyst is something that changes the rate of a reaction without itself being consumed in the reaction. If you think back to our reaction with elephant's toothpaste, our peroxide was decomposing to form water and O2, but the iodide did not appear in this chemical reaction equation. We would typically write the catalyst as we would write other reaction conditions on the reaction arrow. You'll notice that I wrote changes the reaction rate, not just speeds up the reaction. Though many catalysts do speed up reactions, catalysts can also do other things for reactions, including slowing them down or causing one product to be favored over another. For now, though, we're primarily going to talk about a catalyst that speeds up the reaction. The catalyst does that by interacting in some way with the reactants as they go to becoming the product. In that way, you can think of a catalyst a little bit like a machine or a tool. A hammer could help you drive nails to build a house, but when you're done building the house, you still have the hammer. Let's take a look at what that means in terms of the potential energy surface. We already saw earlier on, when we looked at the elephant's toothpaste example, that the catalyst can appear in the reaction rate law. But let's see what it does on the potential energy surface. If we're going from our reactants to our products, the normal pathway might be this one. where we're going to go up some rather large activation energy. That reaction might not be all that quick because the activation energy is so high. Adding in a catalyst opens up a different pathway, typically a pathway with at least one new intermediate that consists of the catalyst attached to one or more of the reactants. That means that instead of having to go over that large barrier, a new pathway is taken, one that involves a different activation energy. As we saw in our discussion of the Arrhenius equation, smaller activation energies lead to faster reaction rates. In the case of a catalyst, it can lower the activation energy of a reaction and thus speed it up. However, there's something else that I should really note as we discuss catalysts. Note that the energy of the reactants and the energy of the products are not changing. That's because the catalyst doesn't appear in the chemical reaction equation. It can't by definition. If it's not in the equation, that means that it's not doing anything to either of those energies. If the energy difference between reactants and products can't change, then that means the Gibbs free energy of the overall reaction, that is the state functions, can't change either. If that state function can't change, then the equilibrium can't change. So, catalysts typically allow reactions to reach equilibrium more quickly, but can't change the position of that equilibrium.